In this video, we're going to be taking a look at the 2025 AP Physics 1 FRQ test. This is version J, the one that was released by the College Board. So our first question, we have a student that has a cart of mass MC and a block of mass 1/5 MC. So basically what's going on is at time equals 0, we have a cart that is moving along with the speed of VC. At t equals t1, our middle picture over here, the block that has a mass of 1/5 MC is dropped onto it, and it does not slide on the cart. And then the final time at t equals t2, the block cart system continues to move to the right with a constant speed, Vf. So we know it is a block cart system. And if we're moving to part A, it says on the axes shown in figure 2, sketch a graph of the magnitude px of the x component of the momentum of the block cart system as a function of time from t equals 0 until t is greater than t2. Now, if the block is dropped onto the cart, it will change the velocity, but it's going to add mass to it as well. In the end, momentum is always conserved if there's no external forces, and since there's no friction acting on it, the momentum is conserved, and we just have a nice flat horizontal line. Now, moving on to part 2, it says derive an expression for the speed Vf of the block cart system after time t equals t2 in terms of MC, Vc, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So I have everything written out in blue over here. I have P naught equal to Pf, saying that the total initial momentum is equal to the total momentum at the final conditions, and I put COM for conservation of momentum. As we said, the momentum is conserved with no external forces. So our initial momentum, MC times VC, equals our final momentum. Our final momentum is MC, mass of the cart, plus the 1/5 MC from the block dropped on it, and then times Vf for our final velocity. When you set those two equal to each other, the MCs drop out, and then once you scoot the 6/5 over to the other side, the fraction flips to 5/6 VC, and that equals our VF. For part 3, it's asking you to find the delta K. So it just says derive an expression to find the change in kinetic energy of the block cart system. And then it says begin your derivation by writing a fundamental physics principle or an equation from the reference information. All right, so we're going to start off with delta K equals K final minus K initial, and we just have to use 1/2 mv squared. So we're going to do 1/2. The mass of the block and cart together is 6/5 mc, and we just got the VF, so we slid that right in there, and then we're going to square it. So that whole thing becomes squared. So remember, the 5/6 gets squared and the VC gets squared as well. And then we're going to subtract the initial kinetic energy. That's just regular 1/2 MC VC squared. Now, when you do that and you multiply all these fractions together, you get 15/16 MC VC squared. And then to get a common denominator, I turn my 1/2 into a 18/36. So when you subtract those fractions, 15/36 minus 18/36, you get negative 3/36. And then that's the coefficient in front of the MVC squared. As you see, this one has an MVC squared, and this one does as well, which works out nicely. And then negative 3/36 simplifies to negative 1/12. And then our final answer is negative 1/12 MC VC squared. Now, there is a little loss of kinetic energy because energy is not conserved because there is an inelastic collision, although momentum is conserved. Moving on to part B, this check got moved over a little bit, but this one remains constant. So they're saying that the case is a new block that's dropped and then collides with the top of the cart, and the new block slides along the cart but does not slide off the cart. the time interval from when the new block collides with the cart and moves together with the cart is delta t. During delta t, there's a frictional force between the new block and the cart. So there's some parts that might throw people off a little bit, talking about sliding and friction and things like that. But remember, our block and cart together are the system. If it's all within the system, then there's no external forces coming from the outside. So determine whether the x component of the momentum of the new block system increases, decreases, or remains constant during delta t. Remains constant, no external forces, and the momentum is conserved in this case because everything is within our system. Now, going to question number 2, a block of mass m is released from rest at position x equals 0. I won't do all the reading here. You can kind of see it from the picture that at x equals 0, that's where the block is at rest. It starts to accelerate down the ramp and then starts hitting the spring and compressing it. It says at x equals 8d, that's when the block makes contact. And then I have this part boxed in red already. It comes to rest at x equals 12d. All right, so let's go ahead and jump ahead and we're going to draw some energy bar charts. So it says the shaded bars should start at the dashed line that represents zero energy, represent any energy that is equal to 0 with a distinct line on the 0 energy line, and the relative heights of each shaded bar should reflect the magnitude of the respected energy consistent with the scale used in figure 4. Okay, this is an important part. When something has 0, you want to make sure you have a distinct line to show that it's 0. All right, they gave us a huge hint in our first one. We have kinetic energy right over here of 7 E naught. We have a UG of 2 E naught, and then we have a spring potential energy of 3 E naught. Okay, so 7 plus 2 plus 3 is going to give us that 12 E naught total. So we know that our total energy is going to be 12, which means we need to have 12 bars of energy in our first and second graph because it says everything is within the system. It says block, spring, earth system. So it says right over here, block, spring, earth system. So that's basically everything. And then there are no there's no work done on anything done on the system or by the system. So all of our 12 E naughts of energy are going to remain in different forms, but there's going to be 12 total. All right, so let's go to our x equals 0 position. So that's where it's at its highest position. There's no velocity, no kinetic energy. The spring is not compressed, so all 12 go to our UG. And we have the distinct line right here for our K, and we have a distinct line for our US. Now, going to 6D, that is half the diagonal distance down the ramp, and it is also half the vertical distance down the ramp as well. So what I thought about in my head is we have an unknown theta, but say, for example, that theta was 30. If you take the sine of 30 times the length that it moves down the ramp, that would give you the vertical distance or the height the block is at. So sine theta times 12 would be a height of 6. And then sine theta times 6d would give you 3. So it does drop to half the height. So I did that little double check in my head. All right. So with that being said, since it's dropped half of its height, you could see here that my UG goes up to 6, and then the rest is pretty easy from there because it hasn't touched the spring yet. So I definitely have a distinct line at 0 for my US, my spring potential energy, and then the kinetic energy would definitely have to go up to 6 as well so that we have a total of that 12 units of energy as we did for our third graph and our first graph. All right, let's go ahead and move on to the next part. It says that figure 5 shows block x equals 0. The block is released from rest, and the block at x equal 12 released from rest, and the block at x equals 12d when the block momentarily comes to rest against the compressed spring. So it is all gravitational potential energy, which we know as mg delta y or mgh, and then it becomes all spring potential energy, which is all 1/2 kx squared. All right, so sliding up here, this is where I put my work. So for gravitational potential energy, it's mg times delta y, or the height. So like I said before, it's sine theta times basically your hypotenuse of 12d, which is the diagonal length of the ramp, and that equals 1/2 kx squared. Okay, now I put 4d because remember it started to contact the spring at 8d, and then it came to rest at 12d. So the amount of compression it got was a distance of 4d. So when you go ahead and square that, that becomes, whoops, that becomes 16d squared when everything gets all squared. All right, so if you take the 1/2 and multiply both sides by 2, that brings a 2 right next to the mg, and then you divide both sides by 16d squared. You can see my 16d squared dropped right underneath in the denominator. One of the d's drops out, and then your numbers are 2 and 12 on the top, which is 24, and has 16 on the bottom. That fraction simplifies down to 3/2, and then you have 3 mg sine theta divided by 2d, and that is equal to k, your spring constant. For C, it says figure 6 shows a graph of the energy of the system as a function of the position of the block from x equals 8d to x equals 12d. So the whole time that the spring is getting pushed in, and you have some spring potential energy. All right, so it says sketch and label a line or curve that represents the total mechanical energy for the block spring earth system as a function of the position of the block from 8d to x equals 12d. So I put a nice straight line here in red. I mean, it's not that straight, but it's meant to be straight, showing that 12 E naught total, just like my bar graphs. So that is my E total. So I made sure I sketched it and labeled it. Secondly, it says sketch and label a line or curve that represents the gravitational potential energy. Whoops, kind of cross that out. Gravitational potential energy for the block spring Earth system as a function of the position of the block from x equals 8d to x equals 12d. Now, each time the spring gets compressed 1 unit of it's saying it's 1d, I guess. So from 8d to 9d to 10d, it is decreasing its height by 1 unit as well. So it is a linear decreasing curve. So it's going to start from 4e. So I know that because it started with the full 12 of energy, and then if it slid down to the 8D position, okay, then it would drop 8 units of energy. So this is when it has no movement at the very beginning of the ramp. And then when it slid down 8 units of energy, it lost 8 E naughts basically. And then it's going to start from 4 E naughts. And then once it reaches its base position, the gravitational potential energy reaches 0. So I have a straight line that goes from 4 to 3 2, 1, and then 0. Okay, and I wrote straight because I didn't do a good job of drawing a straight green line. For part D, it says indicate whether the speed v9d of the block at x equals 90 is greater than, less than, or equal to the speed v8d of the block at x equals 8d. Okay, so my first inclination is to say that at the lower position, v9d is greater than v8d. Now, I want to make sure I find some evidence that supports that. So it says justify how your response is consistent with energy lines or curves you drew in figure 6 in part C. All right, so let's slide back here. Now, if we have 4 units of gravitational potential energy at that point, to fill up our full 12 bars of energy at that point, our kinetic energy would be 8 E naught. Now, when it goes to position 90, it goes lower on the ramp. So naturally, we would think if it loses gravitational potential energy, it's going to gain kinetic, and it's a total no-brainer that it's going faster at position 9D. But at that point, we have more spring potential that's introduced. So we have 4 units of gravitational potential energy, and then kinetic filled up the additional 8. Over here, we have 3 units of UG, and then we have, it looks like, slightly less than 1 unit of US, the spring potential energy. Okay, you can see the little cross-sectional area over there. So because I can tell it's a hair less than 1, if something slightly less than 1 is added to 3, then we have a number slightly less than 4. Therefore, this line over here is going to be about 8 E naught, but it's going to be a little bit greater. All right, so sliding down over here, justify response, conservation of energy, 12 E naughts total. I would have been a little bit more thorough writing sentences, but I just did an abbreviated version here. At position 8D, my UG is 4 E naughts. Therefore, my first K, called it K1, equals 8 E naught. At 9D, my UG equals 3 E naughts plus a spring potential energy that is less than 1, which was very slightly less than 1. Therefore, my total of those two is slightly less than 4 E naught. That means that my K2 is slightly greater than 8 E naught. And if K2 is greater than K1, then my V2 has to be greater than V1. As I said, if I was doing the real justification, I would definitely have written that out in a few sentences. All right, moving on to question 3. There's quite a bit of reading over here. I'll just kind of sum it up for you. You can kind of tell what's going on with the setup. We have a meter stick. It's connected to a spring scale, and we have some unknown mass that you can hook in these different holes here. So A, describe an experimental procedure to collect data that would allow the students to determine not include any steps necessary to reduce experimental uncertainty. All right. So what we can do is we can come up with a procedure where these have equal torque by pulling the spring scale down a certain amount, and then balancing out this block that would be hanging from these different holes that are in our meter stick. All right. So here's what we would do. Um, I didn't write out every single step for the experiment, but I'll kind of explain what I would be writing. I would have an independent variable that is the varying distances of m naught. We have these 4 different holes like we discussed before, and we want to make sure that we don't write down 60, 70, 80, and 90 because those aren't distances from the pivot point. So we want our lever arms, which is the distance from the pivot point. So the center of the meter stick would be 50. So at my 60 would be 10, my 70 would be 20, my 80 would be 30, and then so on. So I would have a step in my procedure that mentions something along those lines. So I'd have a distance of m naught, and I'd make sure that is from the pivot point. All right, secondly, my dependent variable would be the torque. The torque would be the force from the spring scale. So this F over here is our force from the spring scale, and then its lever arm is always 50 centimeters because it's a full 50 from our pivot point from 0 to 50. Now we can go ahead and hang the mass from those different holes, pull a spring scale until the meter stick is as level as possible, and then record our force from the spring scale. And then to reduce uncertainty, I would repeat and average to reduce uncertainty, put the spring scale or pull the spring scale, excuse me, at each different position, and then level it, and then repeat that whole procedure again to do some averages. All right, from there, we can determine M naught. The way we would do that is we would describe how the data collected in part A could be graphed and how that graph would be analyzed to determine M naught. Now, what you would do from there is you would plot torque versus distance. And if you did that, anytime you find a slope, your slope is basically going to be your change in y over change in x. So if we take a look over here, if we did that, it would basically be torque divided by distance. And because torque equals force times lever arm, then we are basically taking torque divided by our lever arm, and that would equal the force. And the force is going to be equal to m naught g. So if we find our slope and then divide it by g, that would give us our m naught. So it says slope equals m naught g, take our slope divided by g, and that would give us m naught. So that would be how we would use our data, graph it, and then at the very end, you would take your slope and then divide it by g to give you your final answer. All right, moving on, we have a case over here where we have an axle and then we have a spring scale, looks like basically showing the force of tension. And then you can move the cable over here at different angles and then get various tensions. As you can see here, as our angle increases, our tension decreases. All right, let's see what they want us to solve for here. It says the students correctly determine that the relationship between ft and theta is given by ft equals 5 mg over 6 sine theta. The students create a graph with 1 sine theta plotted on the horizontal axis. It says indicate what measured or calculated quantity could be plotted on the vertical axis to yield a linear graph whose slope can be used to calculate an experimental value for the mass of the meter stick. All right, if you're taking a look at this relationship that I boxed over here in green, ft equals 5 mg over 6 sine theta, it would be the most reasonable thing to graph ft on your vertical axis because capital M is what we're looking for and it's constant, and obviously g is a constant as well, so there's not really any variables to look for besides ft, and we had a spring scale to find our ft anyways, so ft definitely seems like the way to go. Now it says on the blank graph provided, create a graph of the quantities indicate in part C that can be used to determine M. And it says use table 2 to record the data points or calculate quantities that you will plot. Clearly label the vertical axis, including its appropriate units. Plot the points you recorded in table 2. All right, so table 2, they already told me my x variable was 1 over sine theta, so I stole all the thetas from the previous table and I just plugged them in and did 1 over sine theta 5 different times. Here are my 5 values, and I just took all of the FTs directly from that previous table as well. I plotted 5 points and I expected them to be linear, but not perfectly linear because they want to usually make sure you know how to draw a best fit line. So I didn't really use a straight edge here, as you can tell, but I tried to squeeze a line here the best I could. And I made sure I put FT in newtons on the side. And I also put a title there just in case, FT versus 1 over sine theta. All right, so I recorded my table data in table 2. This is my table 2 over here. I labeled my vertical axis as appropriate, and I plotted the points. I also put in my best fit line, just kind of, centered it the best I could amongst all the points. Now it says use the best fit line that you drew in part C to calculate an experimental value for the mass M of the meter stick. All right, here's a part that's a little tricky. We have the rise over the run. The rise is the ft divided by the run, which is 1 over sine theta. All right, so that's basically what your slope is over there. And anytime you take something divided by a fraction, it's the same thing as multiplying it by the reciprocal, which means that this is basically the same thing as ft sine theta. Now, with that being said, I'm going to go back up here because they gave me a relationship to work with. Now, if I take the setup they gave me here and I cross multiplied the sine theta up to the left side, then it becomes ft sine theta on the left side of the equation, which is my slope that I just mentioned. And then I have 5 mg, and then we got the 6 on the bottom here. So our slope is equal to 5/6 mg. Now we want to solve for our m right here. That's our main goal. So if we move everything to the other side, we could divide both sides by g, which would just place a g underneath our slope. Remember, this whole chunk is our slope. And then once you move the 5/6 to the other side, it becomes 6/5 once you cross multiply it over to the other side. So our capital M is going to be 6/5 times our slope divided by G. All right, so what I did here is I picked 2 points. I know they're not perfect because my line was definitely not perfect by any means. But let's go ahead and look at what I got here. So I'm about at the origin, close enough. So I put 0, 0. And then I identified a point over here right at the end where it looks like it's 2.6 as the x coordinate. And then it's up slightly above it, maybe 2 boxes. So 2.6 and then 22 for my y coordinate. So I use that. My origin, 0, 0, and 2.622. Found the slope of that. I got 8.46 newtons. Okay, that is my slope. Just a moment ago, I said when I did the rearranging, it's 6/5 times the slope divided by g. So I just did a little bit of math. I did 6/5 times the 8.46 that I slid down into here, divided by my constant g, and that equals my capital M. For my final mass, I got 1.04 kilograms. I'm sure that's definitely not perfect by any means. My guess would be if you had any reasonable mass near 1, that would probably be accurate enough. All right, moving on to question 4. In scenario 1, a swimmer holds a block, mass M at rest. We got mass M at rest in a tank of fresh water with a density rho 1. The block is released from rest and accelerates upward with an initial acceleration a1. All right, so basically what's happening here is, of course, this is a buoyant force type problem. We have an FB going upwards. I drew my vector slightly larger, and then we have an FG going down, and that's going to be accelerating upwards because our FB is greater than our FG. Now it says that in scenario 2, the swimmer holds the same block at rest in a tank of salt water with density rho 2, where rho 2 is greater than rho 1. The swimmer again releases the block from rest, and the block accelerates upward with an initial acceleration a2. All frictional forces are negligible. All right, so if you look at A is over here. It says indicate whether A1 is greater than, less than, or equal to A2 by running one of the following in your answer booklet. So I have A2 is greater than A1. Justify your answers in terms of all forces exerted on the block. And it says use qualitative reasoning beyond referencing equations. All right, so again, my answer is a little bit abbreviated, but we have the net force, which is M times A, equal to the buoyant force upwards minus the FG downwards. So MA equals rho VG minus FG. And I said if rho 2 is greater than rho 1, then my buoyant force 2 must be greater than my buoyant force 1 because rho Vg is the product of 3 numbers that obviously includes rho that gives us our FB. So FB2 must be greater than FB1. And then if you have more buoyant force, then you have more net force, and that equals more upward acceleration. So I would have written some of those things down along with a few sentences to back up some of my work. Now for B, it says, consider the general case where a block of mass M and volume V is completely submerged in a fluid of density rho, starting with Newton's second law, derive an expression for the initial upward acceleration A of the block when the block is released from rest. Express your answer in terms of M, V, and rho and physical constants. As appropriate, begin your derivation by writing a fundamental physics principle or an equation from the reference information. All right, so I start off with Newton's second law right over here. Okay, again, I knew that the sum of the forces was my buoyant force minus my Fg, so then I expanded those out into rho Vg minus mg. The g got pulled out in front, got factored out, and then I have rho v minus m. Okay, the rho is circled over here to prove a point for part C, which I'll get to in a moment. And then because of the initial m there, there's an m in the denominator. So A equals G, parentheses, rho v minus m over m. For part C, indicate whether the expression for the acceleration you derived in part B is or is not consistent with the claim made in part A. Briefly justify your answer by referencing your derivation in part B. So that's where I'm talking about this part over here. So it is consistent. If the rho is bigger, then the FB is bigger, then the acceleration is larger. And you could talk about how this rho over here would make the numerator greater overall. And if the numerator was greater, then mathematically your overall number and acceleration is going to be greater. So again, I would point to certain parts of that formula, and then with my justification, I would add a few sentences. All right, so that does it for all 4 questions for the 2025 AP Physics 1 FRQ section. In the comments, let me know how you did. Tell me how many of those 4 you think you did well on. Hopefully you did really well. Good luck with your results, and thank you for watching and listening.